Hi, welcome to our next lecture on Note Packet 21. We're going to be talking in today's lecture in our textbook about section 3.8, which is on the content of implicit differentiation. And there are two major takeaway lessons from this. One is how to use implicit differentiation to find the slope of the tangent line to an implicitly given curve, and that's what we're going to start with. And then the last thing is the derivatives of inverse trig functions. There's one additional thing that we're going to do together also, which is more related to this point right here, which is that we're going to learn how to find higher order derivatives to implicitly given curves as well. And we'll call it good at second order derivatives, so the method works in general. Okay. So our first thing that we need to do is we need to talk about what does it mean for a variable to be implicit, so that we have a signal that we should be doing implicit differentiation. And so I wanted to first start by focusing on this thing that we sometimes write. Sometimes we write something like S equals S of t to remind ourselves that the symbol S is actually a function of t, even though in some expressions where I use S, I'm not explicitly indicating that that we have a function of t right there. So I think the best way to illustrate this is with these two things right here. So if we look at the expression for f, that's this one right here. If we look at the expression for f right here, I want you to note that just looking at f, we don't see that f actually depends on time. That relationship is implicit. That dependence is implicit. So by writing that S equals S of t, this thing right here reminds us that S equals S of t, that the symbol is that symbol S is actually a function of time, and thus f equals f of S of t, and so ultimately f is a function of time, even though when we wrote it down here, it looks like it's just a function of S, but it's actually a function of time because S is a function of time itself. So one way of reminding ourselves of that would be when we write what f is equal to, specifically to put S of t there to indicate that that dependence is there. So this is not multiplication by t, but dependence on t. And I really want to be able to take the derivative of f with respect to t, but there's this thing in the middle. There's this S in the middle right here. So I really want to write down what df dt equals. And in order to do that, I need to take ddt of s squared plus 1. And this is where the skill comes in, because s is a function of time, and this is where we're going to be doing the implicit differentiation. Okay? So, how do we actually compute this expression right here? What we need to do is we need to use the chain rule to take the derivative. And so whenever so we're going to take the derivative of this expression. So we're going to take d dt of s squared plus 1, and we're going to use we're going to take the derivative with respect to s kind of as normal. So we're going to take the derivative as we expect, and we're going to get 2s. But then that's times ds dt, and that's because when we take the derivative of this part right here, this is just something squared, right? And when we take the derivative of something squared, we have to chain out the derivative of the inside. And in this case, that part is, I have this thing right here, and then I need to chain out its derivative, and I get ds dt. And the thing that maybe seems a bit weird about this is that this thing right here, ds dt, as stated on the screen right here, I don't know what this value is. But maybe it's given, or maybe I know. Maybe I happen to know the value of s, and then I can solve for ds dt. And that's very often going to be the case, both for the problems that we're going to do in this section on implicit differentiation, as well as on the section for doing related rates problems. So it's kind of a preview of implicit variables and implicit differentiation. So let's turn the page. So we're focusing our attention in large part in this section 3.8 on curves that are given implicitly. And the one that you're going to be most familiar with is the unit circle. X squared plus y squared equals 1. So I've got this relationship between x and y, and they're coupled in this sense. And they give a curve in the plane, and what I'm going to draw is a pretty mediocre circle. Could have been worse. Is a circle, and this is the set of, so this circle is the set of points x and y such that x squared plus y squared equals 1. And so it's this really special set of points. There's no other set of points that satisfies that constraint. Let me go ahead and label my axes as well. So that's where 1 is. This is where negative 1. Let's put x there and y there. So this is still a curve, and it's just not a function, right? This thing fails the vertical line test. If I draw a vertical line like that, this curve fails the vertical line test, and that's because there are two branches that we have to follow. There's a positive branch and a negative branch, and we could spend time talking about how to find these things, but we're not going to do that in this class. So we're not going to talk about how to come up with this picture. we're going to talk about how do I come up with the slope of the tangent line through a point on this curve, thinking about it as a curve. So if I'm right here, and let's go ahead and label that point to be x naught comma y naught. We want to be able to answer the question, what is the slope of that line? This right here is the tangent line to f at x naught comma y naught. And it's well defined. And we want to be able to find the slope of that line. Because then we could write the equation for that line, and this is kind of a common thing that we do in the world of Calc 1, is we find slopes of tangent lines. That's one of our fundamental operations. Let's back up and make an observation. I want to make an observation. If I give you an x, you can find a y. You'll find two different y's. You'll find either a positive one or a negative one. But if I give you an x, you can find a y. That means that y, we could think of it as being a function of x. Like, for example, I could be like, well, let's let x equal minus a half. Then we could ask, what's y? Well, let's go ahead and try it. I'm going to have minus a half squared plus y squared equals 1. Minus a half squared is a quarter, and I'm going to move it to the other side by subtracting, and I'll get y squared equals 3/4, which means that y is equal to positive or negative the square root of 3 over 2. So I gave you an x, and we found a y. So that is to say, the big point here is that y is implicitly a function of x. So now what I'd like to do is I'd like to practice implicit differentiation with you. And I'd like to find an equation for the tangent line, or the slope of the tangent line at any point x naught comma y naught. So let me transcribe our equation, x squared plus y squared equals 1. And note that if this is true, then it must also be true that d dx of x squared plus y squared is equal to d dx of 1. Because if I have two things that are equal to each other, then their derivatives must be equal to each other also. So what I'm doing in this step is I'm differentiating both sides. And we'll just kind of let things be what they are. On the right-hand side, I've got the derivative of 1, which is 0. And on the left-hand side, I've got the derivative with respect to x of x squared plus d dx of y squared. The derivative with respect to x of x squared is 2x. And the derivative with respect to x of y is 2y times dy dx, because I have to chain out the derivative of the inside from the chain rule. Because I have that y is a function of x. Chain rule says that when I'm taking the derivative of something with respect to some other variable, I have to be careful to chain out derivatives with respect to that variable. Now, this expression, dy dx, that I have right here, this is the name for the slope of the tangent line. This is the name of the thing that I want to find. So let's solve for it. Let's solve for dy dx. So let's move the 2x to the other side, and I'll have 2y dy dx is equal to minus 2x. Let's cancel the 2's, and let's divide by y, assuming y is not equal to 0. Then I have that dy dx is equal to minus x over y. And more specifically, if I try plugging in some specific point, x naught, y naught, then it tells me what the slope of the tangent line is. So the slope of the tangent line is equal to, so the slope of this line, slope of that line is dy dx, that's been our name for the slope of the tangent line for quite some time, and we derived a formula that's minus x over y. Now, let's check and see whether we get something sensible. So what if I try plugging in this point right here? That would be the point 0, -1. Our tangent line is horizontal, so the slope is 0. Let's double check that we actually get that with our formula. Let's do dy dx evaluated at x comma y equals 0 comma -1. That's equal to minus 0 over -1. What do you know? We get 0, which is exactly what we got because we had a horizontal line. Now it would have been true even if I had a positive or a negative right there, because it's 0 at both of, the slope of the tangent line is 0 at both of those points. So the formula that we just derived lets us find the slope of the tangent line at any point on this curve except for these two special points out here. And that's where the tangent line is going to be perfectly vertical and we get infinity for those two things. Okay. So reviewing the steps that we did, what's a good color for me to use? Let's try peach. So here, I just have the equation I was given. Here, I differentiate both sides. And that kind of goes on to the next step right here, as well as this one right here. It's very important that we remember to chain out from the chain rule anytime that you take the derivative of something with a y in it. Then we solve for dy dx. And then boom, I have my formula. And then optionally, plug in your x, y coordinates to get your concrete value. Okay, I'm going to go ahead and turn the page. So let's do another one. I'm going to do this without a picture, because we don't actually need a picture in order to do this. It can help because then we know whether we're supposed to be getting something that's like positive if it's going up, or negative if it's going down. But we can do it without. We can do it without that. So as a first step, I like to sometimes be really explicit in looking at the original equation that I was given right here. So this governs the set of x's and y's on the curve. I might go ahead and, depending on whether I need this reminder or not, write down something like y of x to the fourth plus x times y of x equals x cubed minus x plus 2 to remind myself that y is a function of x and that I'm going to have to chain out a derivative of y with respect to x whenever I take the derivative of those pieces right there. So whether you find that helpful or not, I think is up to you. So let's take this expression, this equality, and differentiate both sides with respect to x. So let's take dy dx of y to the fourth plus xy. That's equal to dy dx of the right-hand side, x cubed minus x plus 2. So we're going to differentiate now. So the derivative splits across that sum. And so I just need to have y to the fourth, the derivative of y to the fourth with respect to x. So I get 4y cubed, and now I took a derivative of a y, and so I've got to chain out a dy dx. I don't know what that is, but that's what we're finding, and that's okay. Plus. Now we're going to use the product rule on this one right here. So the derivative of the first times the second plus the first times the derivative of the second. In this case, is just dy dx. That is equal to, now we're going to go ahead and do the derivative of the right-hand side. This is exactly what we would expect. It's just a derivative of an expression pure in x with respect to x. So I get 3x squared minus 1. And now my objective, after doing that, is to solve for dy dx. We could simplify if we wanted. We could try to do some simplification with this line here. But we're going to now do step 3, solve for dy dx. And so I'm going to take and put everything with dy dx on the left and without on the right. So that means that I've got to take this 1 times y, and I've got to move that to the other side by subtracting it. And so I'll have that 4y cubed dy dx plus x times dy dx is equal to 3x squared minus 1 minus y. And this is really common that you're going to find this. So now we're going to have to factor out these two terms, these two dy dx's, because everything on the left is going to have a dy dx, and everything without it is going to be on the other side. So we're going to factor it out, and we'll find that dy dx times 4y cubed plus x is equal to 3x squared minus 1 minus y. And then finally, we will divide that to the other side. We factored out. So we'll divide that to the other side, and we'll find that dy dx is equal to 3x squared minus 1 minus y over 4y cubed plus x. Okay? And this thing right here is the formula for dy dx, or y prime, or the slope of the tangent line. So we can figure out what that slope is at some particular point. Let's unwind a bit. What point were we interested in? We were interested in the point p equals 1, 1. Point 1, 1. So we have dy dx at 1, 1. I love vertical bar notation. Is equal to 3 times 1 squared minus 1 over 4 times 1 cubed plus 1. So in the top, I just have 1. In the bottom, I have 5, 1/5. So that's the slope of the tangent line. And if we want to get, as a last step, the equation for the tangent line, then we're going to use point slope form. So point slope form is y minus y naught equals m times x minus x naught, where m is the slope, and we just found that. We found that that's 1/5. And y naught, x naught, or x naught comma y naught is our point that we were given. So we have that y minus 1 equals 1/5 times x minus 1. And now we're going to solve for y, because we want it by itself. Y equals 1/5 minus 1/5 plus 1. Oop, forgot my x. And then finally, I find y equals 1/5 x plus 4/5. That is my equation for my tangent line to my curve at the point 1, 1. Okay, let's turn the page. So let's do another example, and hopefully you'll start to see the pattern in these problems. I think there's a pretty strong pattern, and I find it really satisfying. So we're not going to write the equation for the tangent line for this one. We're just going to find the slope of the tangent line. So I've got this equation, and the first thing that I'm going to do is I'm going to differentiate both sides. So if e to the x minus y equals 2x squared minus y squared, then it must be true that I better give myself, I don't know how much space I'm going to need for this. I don't think a whole lot. D dx of e to the x minus y is equal to d dx of 2x squared minus y squared. So let's take the derivative of the left-hand side. The derivative of e to the is e to the, and then I've got to chain out the derivative of the inside. So now we've got to put here the derivative with respect to x of x minus y, 1 minus dy dx. Again, this part right here is x minus y prime. And on the right-hand side, I'll get 4x minus 2y dy dx, right? Every time you take derivative with respect to of a y expression with respect to x, this thing just keeps popping out. Boop. So when you're doing this, anytime you take a derivative with respect to of a y expression, be sure to chain it out. And now I want to solve for dy dx. And if you find writing dy dx a bit burdensome, I could just call it y prime. It's up to you. So let's go ahead and put everything that has dy dx on one side and not on the other. And let's start by distributing this across this quantity. Because one of them, the e to the x minus y times 1, is not going to have a dy dx, but the other one is. So I better distribute, and I'm going to have e to the x minus y, e to the x minus y, minus e to the x minus y times dy dx. Or if you find that burdensome again, I can write y prime equals 4x minus 2y y prime. So let's move that one to that side, and let's move that one to that side. So I'm going to have 2y y prime minus e to the x minus y y prime equals 4x minus e to the x minus y. So I've got y primes here. We're going to factor them out. That's a super common step. Like, that's going to happen all the time in these problems. So I'll find that I have y prime equals 2y, nope, y prime times 2y minus e to the x minus y is equal to 4x minus e to the x minus y. And now let's divide. And we'll finally have our formula y prime equals 4x minus e to the x minus y over 2y minus e to the x minus y. Okay, so we're able to find our formula for the slope of the tangent line, but we wanted it at the point p equals 1, 1. And so now I need to plug in y prime evaluated at 1, 1, and that's equal to 4 times 1 minus e to the 1 minus 1 over 2 times 1 minus e to the 1 minus 1. So e to the 0 is equal to 1, and that expression appears twice. So I have 4 minus 1 over 2 minus 1 is equal to 3. Okay. And that's the slope of the tangent line at that point. So I want to show you a possible shortcut. So I want to find with you, we've changed up the variable names a little bit here. Instead of x, I have t. Fine, it doesn't matter. I'm gonna show you a shortcut. So we're gonna start with the original equation that we have, y times cosine of y plus t squared. That's equal to t cubed. So I'm going to start by differentiating that with respect to t. So I'll have d dt of y times cosine of y plus t squared equals d dt of t cubed. I've got a product right here. And so I'm going to do the product rule on it. So we'll have, let's see here, the derivative of the first is y prime times cosine of y plus t squared plus y times, now the derivative of cosine is minus sine. And now I've got to chain out the derivative of that because of the chain rule. So that's times y, this times y prime plus 1 plus 2t. And that whole thing is equal to 3t squared. Okay. I don't really want to go through the trouble to solve for y prime here without doing a thing. So rather than solve for it and find a formula, what I'm going to do, so instead of finding the formula for y prime, let's now plug in our point p equals 0, 5 pi over 2, and then solve for y prime. I think you'll find that this is quite nice. So I'll have y prime times cosine of, let's see here, 5 pi over 2, that's what y is, plus 0 squared, plus 5 pi over 2, that's this y right here, times minus sine of 5 pi over 2, plus 0 times y prime plus 1 plus 0 equals 3 times 0. So everywhere I saw a t, I put in 0, and everywhere I saw a y, I put in 5 pi over 2. Let's go ahead and simplify this expression. So let's simplify. Y primes are just y primes, but I have cosine of 5 pi over 2 plus 5 pi over 2 times, let's go ahead and move that minus sign right here out front so I don't lose track of it or start subtracting, times sine of 5 pi over 2, and that is times y prime plus 1, that's equal to 0. Okay, so now I think I'm in, this feels far more comfortable to me. So let's go ahead and take this and distribute it across. Yep. Y prime, we'll see here, cosine of 5 pi over 2. Cosine of 5 pi over 2. I want to stop writing that. Let's do a unit circle. Let's see here. Pi over 2. 2 pi over 2. 3 pi over 2. 4 pi over 2. Okay, 5 pi over 2. And that point right there is, we'll see here, that point is 0, 1, which means that cosine of 5 pi over 2 is equal to 0, and sine of 5 pi over 2 is equal to 1. So this is equal to 0, and that is equal to 1. So, oh, that is so nice, because you know what that does? That makes this y prime times 0 minus 5 pi over 2 times 1 times y prime plus 1 equals 0. Oh, that's so nice. So now I'm going to erase, I'm just going to take out that times 1 because that's not helping me. Okay, now I'm totally down with this. I think I'm going to distribute this now. Okay. Yeah, now I'm ready to distribute that. So now I'll have minus 5 pi over 2 times y prime minus 5 pi over 2 equals 0. What's plus 5 pi over 2 to both sides? So I'm going to have minus 5 pi over 2 y prime equals 5 pi over 2. Divide. That means that y prime is equal to minus 1. Oh my god, that was quite the thing. So I just want to point out in that process, like, it's just kind of like, these are kind of plug and chug problems in a sense. So the main points that I want to point out to you are like when doing the derivative here, you just got to be really so super careful when doing those to be careful to use the product rule, quotient rule, and chain rule, because it's easy to forget, like at the point that we're doing this one right here, that I have a product of two things. It's easy to forget that. Okay, so the second thing that I want to point out about what we did, what was so nice about it, was this thing right here. So instead of going so that we get an evaluable formula, as soon as I have an equation that, as soon as I've done my derivative, maybe there's some easy simplification, I don't know, but I'm just going to plug in our point to this expression right here. And then that's going to make a whole bunch of stuff easier to work with, particularly in the types of problems that we give in this introductory class. Lots of stuff's going to be 0 and 1 probably, because we're training you. So that's a cool shortcut. So what's the shortcut? Instead of going all the way to finding a formula for y prime that you could put any point into, just go ahead and, after you have your derivative, go ahead and plug in and then solve for y prime. Okay, moving forward. I have a video about this next one here. This next one has us find higher order derivatives implicitly. And so what we're going to do is we're going to find a second order derivative for this equation. So we're going to find a second order derivative. Okay, fine. So we're gonna still do the same thing that we were doing before. The first thing we're going to do is we're going to differentiate both sides, and then I'm going to solve for y prime. Okay, so I'm going to go ahead and skip the step where I write down that I'm differentiating both sides, and I'm just going to go ahead and do it. So if x squared plus 4y squared is equal to 7, this is an ellipse, then it must be the case that 2x plus 4, plus I need to do the power rule on that expression, 8 times y prime is equal to 0. Right? So I differentiated both sides. The derivative of 7 is 0. And I'm going to solve for y prime. So then I have 8y prime is equal to minus 2x. And now let's divide by 8y. And I'll have that y prime is equal to minus x over 4 times y. Okay, so that is an expression for the first derivative, dy dx. And from that, check this out. If I take the derivative of this, we're going to differentiate both sides. It happens to be the case that d dx of y prime is going to be equal to d dx of minus x over 4y. And this thing on the left-hand side is equal to, this thing on the left-hand side right here is equal to y double prime, because the derivative of the first derivative is the second derivative. And that's equal to, now I've got to do the quotient rule. So we'll go low, d high, minus high, d low. Ooh, there was my mistake right there. I noticed it immediately. That's supposed to be for y prime. Draw a line and square below. So this has a y prime in it. And we're going to go ahead and substitute that away. And what are we going to substitute in? We are going to substitute in that thing right there. So we'll substitute in y prime equals minus x over 4y that we found before. Because our goal is equal to, our goal is a formula for y double prime as a function of x and y. So I just get to plug in my coordinates, x and y, and it tells me what the second derivative is. So we'll go ahead and substitute that in and do some simplification. Let's see here, minus 4y plus 4xy prime, and that's where I'm going to substitute. And in the denominator, I have 16y squared. So let's do that substitution. Minus x over 4y. Ooh, I like that. 4 is going to cancel. And we'll get minus 4y minus x squared over y over 16y squared. And we're done. I have a formula for y double prime, second derivative of y, as a formula of just x's and y's. So my 3 steps that I engaged in there were do implicit differentiation for the first derivative. And we got that. Here's the first derivative. Then we differentiate again. On the left-hand side, I just get my second derivative. On the right-hand side, it's very often going to start with a quotient rule. And then we substitute in the formula for y prime that we found before in step 1, and then simplify and done. And we get a formula. Groovy. Let's turn the page. These formulas for the inverse trig functions can all be found using implicit differentiation. I'm going to say that this content is optional for spring 2020, and if you really want to see it, I want you to see the video on YouTube, or find that link through Canvas. And that would be derivatives of inverse trig functions. I don't really want to go through that right now. Suffice it to say that we have these formulas, which let us compute derivatives of inverse trig functions. And I would probably be like, okay, fine, I'll put these on my note sheet, or what other people call their cheat sheet, your reference sheet that you're building as you do this. Because there's a lot. I think that having a reference card for this is sufficient. Okay, let's move to the last page, okay? So I think it's useful to remind ourselves that the formulas that we keep giving you omit the chain rule. And so in these cases, in each of these things, I have the arc sign of whatever, and then you just take and put the whatever inside the formula where on the previous page we had an x. So I had 1 over square root of 1 minus x squared. Here I have 1 over square root of 1 minus blah squared. And then you chain out the derivative of blah, because you got a blah right there. And if that blah is 1, then, is x, then blah prime is equal to 1, and all of this stuff right here, we just hide it. So these formulas on the previous page, these really are general. These really are general formulas. Because chaining out, you'll always just get the derivative of the inside thing, right? Nothing else ever happens with it. You only ever get the derivative of the inside thing. Ooh, that's so nice. Wow. Oh, that was cool. I'm going to do that more. I enjoyed that. Okay. So let's just fly through an example. I'm not going to fly through it. Let's go through an example of one of these problems. So let's take the derivative of the arc cosecant or inverse cosecant of e to the x plus 1. So right there, I've got my blah, and my blah is e to the x plus 1. This last bit right here says that after getting the formula, I don't know what that t is. After we get that formula, we are going to evaluate at x equals 0. Let's see here. So the derivative of arc cosecant is that thing right there with a chain out right there. Okay, so we're going to do that, and my blah is e to the x plus 1. So when I have my blahs, I'm going to substitute e to the x plus 1 for them in that formula. So d dx of the arc cosecant of e to the x plus 1 is equal to minus 1 over the absolute value of e to the x plus 1 times the square root of e to the x plus 1 squared minus 1. And now I've got it here. I'm going to put the derivative of that e to the x plus 1. And so right here, this is all times e to the x, where that's d dx of e to the x plus 1. And then to finish this off, now we will evaluate at x equals 0. So finally, I have d dx of the arc cosecant of e to the x plus 1 evaluated at x equals 0 is equal to minus 1 over the absolute value of e to the 0 plus 1 times the square root of e to the 0 plus 1 squared minus 1 times e to the 0. E to the 0 is equal to 1. So this is equal to minus 1 over 2 times the square root of, let's see here. So this is 2 squared, which is 4. 4 minus 1. Oops, stray mark. So now we'll have, let's see here, square root of 3. And then that all is times 1. And is that worth writing? Probably not. So let's go ahead and finish it off. Minus 1 over 2 root 3. Done. So it's kind of like, it's like any of the other formulas, right? Like, it's like apply the formula and be careful to chain out blah prime. And then after that, evaluate. So these formulas, while they look perhaps intimidating, they're not particularly terrible in the sense that, like, all you do is just, like, choose the appropriate formula, put in your stuff for your blah, and then chain it out. Okay, I'm done. That was a lot. Thank you very much for watching. I really appreciate your time, and I'll look forward to seeing you in class to talk about any questions that you might have about this note packet. Thank you so much. I'll talk to you later. Bye, everyone.